In section 5.3, we will discover some properties of logarithms. We're going to look at several rules, and I'm going to relate them back to the rules for exponents that these rules of logarithms are related to. First, let's look at the product rule for logarithms. For any positive numbers, m, n, and a, where a is not equal to 1, the logarithm base a of m times n is equal to the logarithm base a of m plus the logarithm base a of n. In other words, the logarithm of a product is the sum of the logarithms of the factors. This rule is related to the following rule for exponents. When we multiply two powers that have the same base, such as a to the m times a to the n, we combine this into a single power with that base a, and then we add the exponents. Remember that logarithms, when evaluated, are exponents. So it makes sense that when we're taking the logarithm of a product, we're kind of going in reverse and writing it as the sum of the individual exponents. The next rule is the power rule for logarithms, which states that for any positive numbers m and a, where a is not 1, and any real number p, the logarithm base a of m raised to the p power is equal to p times the logarithm base a of m. This is related to the following property of exponents. When we raise a power, such as a to the m, to another power, such as to the nth power, this becomes a to the m times n power. So here we multiply the exponents. Look at the setup here. We have an exponent here in p, and then the logarithm base a of m itself is an exponent. So it mirrors what's happening here when we're raising a power to yet another power. And what we end up with is multiplication. P is multiplied by the logarithm base a of n, such as what we're doing here when we're multiplying these two exponents, m and n. Let's use these rules for the following example. We're asked to express logarithm base 2 of p cubed plus logarithm base 2 of q as a single logarithm. Well, for this one, we're going to use the product rule for logarithms. In essence, we're going to combine the two arguments. Note that we can only do this if there is a common base for the logarithms, which in this case we do have. They both are logarithms with base 2. So we're going to multiply the arguments, so we'll have p cubed times q. Next, let's look at the quotient rule for logarithms. It states that for any positive numbers m and n, and any logarithmic base a, the logarithm base a of the quotient m divided by n is equal to logarithm base a of m minus the logarithm base a of n. In other words, the logarithm of a quotient is the logarithm of the numerator minus the logarithm of the denominator. You can probably guess which rule of exponents this rule is related to. When we have a to the m divided by a to the n, because they have a common base, we can write this as a to the m minus n power. So recall, logarithms are exponents. Logarithms are the results of an exponential question. So it makes sense that when we're taking the logarithm of a quotient, that it results in the subtraction or the difference of the logarithms, just as we see the subtraction of these exponents here in the exponential rule. Next, we'll look at a base to a logarithmic power. For any base a and any positive real number x, a raised to the power logarithm base a of x is equal to x. What we see here is that we have two inverse operations at hand. First of all, we have a as a base being raised to an exponent written as logarithm base a of x. So this logarithm is asking the following question. What exponent must I place on a base of a in order to get the result x? Well, the power, whatever that answer is what's being written here as the answer. So these two operations kind of ask the same question and then go in reverse, and so you end up with just x. Said another way, the number a raised to the power logarithm base a of x is simply x. Let's practice with the following example. Express as an equivalent expression that is a difference of logarithms. Logarithm base 3 of 20 divided by 7 will be written as logarithm base 3 of 20 minus logarithm base 3 of 7. Sometimes we see parentheses around the argument, around these results, and that might be useful just for clarity, but they're not required when the argument is easy to identify. When the argument, however, includes more than one term, such as x minus 6, then the parentheses are absolutely necessary for clarity. In the next example, we have 3 raised to the power logarithm base 3 of 2x. Here we see that the base is 3 and the base of the logarithm is also 3. Therefore, these two operations reverse each other and the result will be just 2x. Next, we have 10 raised to the power logarithm of t. Note that here there is no base that is written explicitly, which means that the base is an implied 10. In other words, this is a common logarithm of t. Because the base of the power is 10 and the base of the logarithm is also an implied 10, the result here will be just t. In the next set of examples, we're asked to express each of the following in terms of sums and differences of logarithms. We have logarithm base b of a raised to the, a times y to the 5th power divided by m cubed times n to the 4th power. We're going to have to use a combination of the rules that we've just discussed, and it really won't matter what order we apply them. This is a matter of preference. What I like to do first is to take care of the products. And here we have a fraction as well. So I'm going to separate the numerator from the denominator using the quotient rule first. So I'm going to write this as logarithm base b of a times y to the 5th power minus logarithm base b of the denominator m cubed times n to the 4th power. Now for the first term, I'm going to use the product rule. So I can write this as logarithm base b of a plus logarithm base b of y to the 5th power. And then I'm going to subtract, and I'm going to use here some brackets. I'm going to subtract the logarithm base b of m cubed plus logarithm base b of n to the 4th power. Notice that I've put these brackets. I guess I could have also used parentheses because of this subtraction here. I want to make sure that I distribute accordingly. Now, for the second, third, and fourth terms, I have yet another exponent in the argument, and I can use one of the rules above to rewrite these as follows. So the first term will stay the same, logarithm base b of a, plus, I can bring this 5 down as a coefficient, so I have 5 times logarithm base b of y, minus, I can bring the 3 down and I'll write that as 3 times logarithm base b of m. And next I can bring the 4 down, 4 times logarithm base b of n. And I'll go ahead and distribute the negative sign in front of the brackets, and so this will become subtraction. So this 4-term expression is what we're looking for in terms of sums and differences of logarithms using all of the above properties and rules. Now I know I've kind of clouded my next problem here, but let me see if I can just enclose it for clarity. Let's look at the next example. Logarithm base a of the cubic root of a squared times b divided by c to the 5th power. Again, we're going to use a combination of the rules that we talked about earlier, and the order in which we apply these rules really won't be important. It's just a matter of your preference. I think, however, because everything is under that cubic root symbol, I will need to take care of that first. So I'm going to start by writing this as logarithm base a of a squared times b all over c to the 5th power. And then I'm going to write the cubic root as being an exponent of 1/3. I think what I'm going to do next is take each factor inside parentheses and apply the 1/3 exponent. So this will be a rule of exponents for now. Logarithm base a of a, 2 times 1/3 is 2/3. And then times b to the 1/3. And in the denominator, c to the 5th, then times 1/3, that'll be 5/3. That's a 3. All right. Now I think I'm going to use the product and quotient rules. And I can write this as logarithm base a of a to the 2/3 power plus logarithm base a of b to the 1/3 power minus logarithm base a of c to the 5/3 power. Notice that the last term we have subtraction because we had that factor in the denominator. Next, let's simplify one more time. In the first term, we have logarithm base a of a to the 2/3 power. Well, notice here that the logarithm and the base of the argument are the same, and so this will become just 2/3. Next, I can bring the 1/3, that is the exponent of b, out as a coefficient. So I can write this as 1/3 times logarithm base a of b. Here, the base of the logarithm and the base of the power do not match, so this is as simplified as we can go for that one. And lastly, I'll bring down the 5/3 in the exponent as a coefficient, so we'll have minus 5/3 times logarithm base a of c.